So welcome to this webinar. And this is the life cycle assessment of emerging biotechnology, carbon capture and utilization technologies. Thank you for your participation. So this webinar has been organized by the VIVALDI consortium. Hello. Thanks to Lara Totolo, that is from CO2 Value Europe, the events manager, and it's also our VIVALDI dissemination manager. Let me introduce myself. I am Juan Baeza. I'm professor in the Chemical, Biological and Environmental Engineering Department at the University Autónoma of Barcelona. And I'm also the work package leader of work package 2 in the VIVALDI project. VIVALDI project that has the participation of UAB, our Autónoma University as coordinator, and then BOCU, Lulea University, Vito, UFZ, LEITAC, Procession, Beta and University of Vic, and To Value Europe, ILE, Nutrition Science, Avantium, Campaign, BAM, BioAgra, and Novamon. So we have many partners, and in this project, we have been studying different technologies that were related to carbon capture and utilization, which is an exciting area of research. And we want to capture CO2 emissions and converting them into valuable products. So it's a very good opportunity to transform our current fossil-based chemical industry in a more circular production system, carbon neutral economy. So this is a great objective. Well, we don't need to stay there. We need to do even more. This is just a step. Finally, our human activities should be really a CO2 consumer instead of a net CO2 producer. But this is just a first step to make our processes, current processes, with lower CO2 production or even this net reduction. But okay, there are carbon capture utilization technologies, such as biotechnological approaches that we have been using in our project are promising, but we have to look for the overall environmental impact. So the VIVALDI project has been focusing during 4 years in these approaches, different technologies. We have been working in the purification and conversion of CO2, for example, with electrocatalysis to formic acid. I've been working also on nutrient recovery, ammonium and other cations with bioelectrochemical systems to make the process more circular. And we have been working in the bioproduction of organic acids by fermentation using Pichia pastoris. And the original focus was on the production of 3-hydroxypropionic acid, lactic acid, succinic acid, and itaconic acid. And also we have been studying the downstream processing, not only producing, but also downstream, because it can be important also, can give some consumption of CO2. Sometimes it's not taken into account, and we focus only on the production part, but that can be an important part. And also in the industrial validation. So all these processes should be made a way that they can be implemented in the industry. So about these technologies, we are studying different techniques, but we have to think about overall thing and the overall production system that including all the steps from CO2 capture to making the product and to produce the pure product, that they should make sense from an environmental point of view. So it is really better than current practices. So the current practices are really optimized process, many years. So we are fighting against these very well-established processes. And we, for sure, we have some benefits of using the carbon capture and utilization technologies, but we have to be aware of all the side effects of this. So we need to include all the inputs and outputs, and we have to demonstrate really that these processes, new CCU processes, are better than current production systems. So this webinar is about the role of an evaluation, overall evaluation, the life cycle assessment, evaluating low technologies readiness level. So we are working with processes at low TRL. So we have to show at a good point this process will be able to be better than the current ones. And with the help of LCA, we have this holistic framework for assessing the environmental impacts. And we are not looking only to the climate change, but all the entire value chain. So it can help the LCA to identify these potential trade-offs and the use of critical raw materials, resource consumption, and all these things together. So we have 3 expert speakers that will present the real-world examples and discuss strategies for applying these LCA techniques effectively at low TRLs. But first, a slight change in the 3 speakers. We'll start with Stefan Kelvenger, that is a project manager at the German Institute for Standardization, DIN, and he is assisting international researchers in transferring their research results into standardization, and was involved in several European projects like IDUN, Synergy, CO2 WIN. So he can give us some general idea about the techniques. We'll have Anna Petit-Bosch, that is a postdoctoral researcher here at the UAB, and will present the findings on the environmental assessment of ionic liquids and their role in carbon capture. And finally, Jorge Senan, that is head of sustainability assessment and optimization team at the Biotechnology Center, that will explore how LCA, combined with the process modeling and future-oriented scenarios, can inform about the development of these low TRL technologies. And he will focus on the part of production of CO2-based organic acids. So we'll have the 3 presentations, and then at the end we'll have a Q&A session, or just a combined Q&A session. Just you can share your questions through the Q&A box or through the chat, and we will take them, and at the end we will discuss. So I think it's time to welcome the speaker, Stefan Kelvenger. So the floor is yours.
Perfect. Thank you very much. So yeah, I start by sharing my screen. So I hope you can see it. Yeah. Perfect. Thank you. So yeah, thank you for the kind introduction, and good afternoon, everybody. So yeah, I would like to welcome you to the presentation, Standardization as a Tool to Harmonize Carbon Management Activities. So yeah, again, my name is Stefan Kelvenger, and I'm a representative of DIN, German Institute for Standardization, which is Germany's national standards body. So I'm stepping in for Dr. Tim Langhorst from the company Carbon Mines GmbH at very short notice today, as he was not able to join as planned. So yeah, originally he had the plan to provide an overview of international efforts to harmonize LCA methodologies for CCU. I will take a similar approach and present instead to use standardization as a viable harmonization tool. So yeah, maybe just a little bit more my background. So as a project manager for DIN's Research and Transfer Group, the task of my colleagues and I is to advise international researchers on standardization, as well as to initiate standardization activities based on their expertise, for example, from research projects. So yeah, more about this later. And maybe before I start my presentation, an important disclaimer. I am unfortunately neither a technical expert in the field of carbon management nor in the field of life cycle assessments. So just for you to know. And instead, during my presentation, I will shed light on the topic of harmonization through standardization, give you also some impressions on the specification DIN Spec 91508 on the topic of requirements for the life cycle assessment of CCU and CCS technologies, a document which Dr. Langhorst recently also worked on. Now, looking at the agenda, first of all, I will provide you with basic information on standardization, including also information on different categories of standards. Then I will talk about DIN's effort to map out standardization and carbon management, as well as to identify future potentials in standardization. I will also inform you about standardization activities within the research project CO2 WIN Connect, which was funded by Germany's Federal Ministry for Economic Affairs and Energy. So yeah, within the project, 3 pre-standards, so-called DIN specs or DIN specifications, were developed. And as mentioned, I will in particular talk about the DIN spec document on the requirements for the life cycle assessment of CCU and CCS technologies. All right, so yeah, starting with a introduction to standardization. So yeah, actually all of us encounter standardization in a broad variety of situations in everyday life. So sometimes maybe more, sometimes less consciously. The basis of global trade, for example, is the transportation of goods. And cargo ships transport goods across the world's oceans by using standardized shipping containers designed and built for intermodal freight transport. So meaning these containers can be used across different modes of transport, such as from ships to trains to trucks and so on, without unloading and reloading their cargo. So the cargo may include charging cables for electric cars or tools for everyday work. And for all of these goods, it's essential that they commit to certain dimensions and functionalities in order to ensure compatibility and to facilitate trade. Also, the benefit of standardization applies to less tangible activities and procedures to achieve consistency, for example, to meet predefined quality levels and to ensure safety for everybody. May it be directly, for example, as shown in this picture, or throughout every benefit in everyday life. But what exactly is a standard? So a standard is a document established by consensus and approved by a recognized body, such as DIN, for example, on the German level, that provides for common and repeated use rules, guidelines, characteristics for activities or their results aimed at the achievement of the optimum degree of order in a given context. Standards should be based on the consolidated results of science, technology, and experience and aimed at the promotion of community benefits. Okay, so to break this down, standards are consensus-based guidelines in the end, which aim at providing best practices to harmonize procedures in order to achieve set target outcomes. The content of standards is not developed by employees of standardization organizations such as me, but it's actually you as international technical experts who collaboratively work on defining SOPs, or standard operating procedures on different topics. So our task as standardization organization is to manage this consensus building process. Also, we promote public participation in this process to depict the state of the art reliably. As the result of this process, standardization documents provide guidance and consistency for users, all while remaining voluntary to use. So standards do not have the status of a law or regulation, but however, in some cases, legislation of a country may decide to refer to existing standards within a law as a sort of publicly acknowledged SOP in a respective field, for example. So in general, standards are remain voluntary to use. Also, an important principle of standardization is that there must be no double standardization, meaning each topic must only be addressed by one specific individual standard. So this coherence enables interoperability, as users can rest assured that the present standard describes the current state of the art. Also, the consideration of standards fosters safety and quality both indirectly and directly, as processes are better coordinated and risks can be better recognized as such. All in all, developing and complying with standards facilitates, enables, and promotes global trade. Now, to benefit of all of these interlocked characteristics of standards, the continuous involvement of experts is really important. By contributing their knowledge or your knowledge, if you participate for the benefit of society, you as experts really make the difference. Okay, so in the beginning, I already talked about standards and so-called pre-standards or specifications. Now, in general, standards differ primarily regarding the level of consensus required on the y-axis and the development time on the x-axis. There are three different types of documents: consortial standards, pre-standards or specifications, and standards. Now, consortial standards are usually developed within a closed body of experts, which clearly separates them from specifications or standards. This closed body of experts may only consist of members of a singular company or other closed groups. So these consortial standards are not developed under the coordination of a standardization organization, resulting in documents that are likely not made available for the general public nor for the competition. Unfortunately, this approach usually results in the cementation of knowledge. Now, as you may know, standards exist on the national, European, and international level. More in the mechanisms of multi-level standardization in a moment. So standardizations act as a tool for the transfer of the recognized state of the art into standardization, as I mentioned. They are developed by a quote-unquote closed standardization committee that represents all so-called interested parties. Now, interested parties represent different parts of society, such as members of the economy, public sector, consumer protection, trade unions, science and research, and so on. It usually takes 12 to 24 months to develop a standard. And yeah, due to the complete consensus that is required for standards adoption and publication. This complete consensus results in the aforementioned high level of trust from users, as standards are reviewed every 5 years and remain valid until withdrawal, for example, when becoming outdated, difficult or ineffective to implement, or when no longer meeting safety and quality standards. So in theory, they are valid for as long as they really have a benefit and can be applied. Now, looking at pre-standards and specification, also again on the national, European, and international level. On the national level, there are DIN spec or DIN specifications, as I've mentioned. On the European level, CEN workshop agreements or CWA documents, and on the international level, IWA documents. Now, taking a look at DIN spec documents, but this actually applies to specifications on every level. They're especially useful for the transfer of new findings, for example, stemming from research projects into standardization. In contrary to regular standard, specifications are developed by open and temporary consortia. So yeah, this is also a benefit, for example, for the transfer really of new research findings. In principle, maybe to explain on this closed aspects of standardization committees, they are not closed per se, but there is, let's say, a limited number of people who can join sometimes. So, and there are also other limitations when somebody wants to participate. I'd suggest you to contact your local national standardization committee, as the rules, so to say, how to participate are different for each national standardization organization. Now, again, regarding specifications, there is a shorter development time, actually 10 to 12 months, because there is no complete consensus required. For both the finalization and the adoption of the final document. The content of a document may act as a basis for or an input for a standard. So they can be seen as the first step, so to say, towards creating a regular standard, as they can often serve as the basis. For example, for a new standard to be developed or to be included into an ongoing standards development process. Specifications are reviewed after 3 years, and they have a maximum validity of 6 years. So this can be seen as a motivation to proactively initiate the transfer of scientific findings into regular standardization. It's also worth mentioning that there are various agreements between national, European, and international standardization organizations. So CEN-CENELEC on the European level, ISO or IEC on the international level. In general, international and European standardization has priority, so to say, over national standardization. Accordingly, existing or contradicting national standards must be withdrawn when European or international documents are published. Okay, now let's take a look at the current standardization landscape in carbon management. First of all, there are activities on the international level and on the European level. So there are multiple working groups for both technical committees. So technical committee on the international level, on the European level, for example, on the topic of capture, transportation, storage, cross-cutting issues, and so on. I also linked the working groups either by this main link or here by the individual links, so you can access the current activities of each working group, taking a look of what has been or is currently being standardized by these individual working groups. Also, there are, of course, activities on the national level, for example, the German level, which is organized within a mirror committee. So here the mirror committee on carbon dioxide capture, transport, usage, and storage. So the task of this mirror committee is to organize the participation of German experts, again, not of DIN employees, but of external technical experts that develop standards on the German level, and discuss and agree on a common joint approach for the participation and standardization on either the European or international level. Now, this mirror committee specifically is composed of representatives of the national, German national standard committees on water practice and on gas technology, as there's a thematic overlap regarding these topics. Furthermore, DIN has a department of its own on strategic development here in the context of sustainability. So its tasks it's responsible for identifying potentials for future standardization activities in general. So its tasks include the monitoring of changing requirements and frameworks, the derivation of standardization needs, and also to give advice for German standardization committees, in this case, this German mirror committee. Now, another task the main task, as I mentioned, is to identify future potentials for standardization. So I listed here some of the recent potentials that were identified. For example, regarding safety standards, regarding monitoring, reporting, and verification, CO2 accounting, and others. So yeah, just for you to know, the slide deck will also be shared with you, so you will have enough time to really read and take a look at every aspect. I would like to specifically talk about the aspect of CO2 accounting in the context of LCA in a moment. So yeah, they identified the need for strict accounting rules to determine the CO2 reduction achieved over the life cycle of the resulting products and to price emissions accordingly. Now, regarding standardization with a CO2 Win Connect. As mentioned, CO2 Win Connect is a project that was funded by Germany's Federal Ministry for Economic Affairs and Energy, and there were a total of 3 DIN spec documents developed. Before I start with describing DIN spec 95108, I will just give you or inform you about a guideline document, which was really, which was the underlying document for the DIN spec that was developed. So it's the Techno-Economic Assessment and Life Cycle Assessment Guidelines for CO2 utilization by the Global CO2 Initiative. So this document, as I mentioned, developed by the Global CO2 Initiative, it's an initiative that envisions CO2 capture and utilization as a mainstream carbon management solution. They aim to provide leadership necessary to establish the new industry of CO2 capture and utilization through evaluation, research, education, training, and outreach. So as mentioned, they developed this document, which was the basis for the specification. So this is also free to download. Feel free to take a look at it afterwards. So underlying problems that were tackled were that the application of LCA and TEU to CCU were not comprehensively defined and described. Another problem was the comparability of different studies, the validation of underlying data and methods. So CCU-specific methodological challenges were targeted, and also recommendations provided on how to address these challenges in a way to ensure comparability and transparency of the results. There are detailed worked examples and on how to apply the guidelines. Also important to know, TA and LCA remain 2 separate approaches in the guidelines as currently common practice, which was also taken into account when developing the DIN spec document. And as I mentioned, so basis for the DIN spec document, and the guidelines are based on the existing ISO 14000 series on LCA, other guidelines, best practices, etc. So referring to the DIN spec document itself, again, based on the ISO 14000 series, which sets out requirements for environmental management systems with little flexibility for different use cases. So it's not feasible to develop separate LCA standards for every technology. This is why the STEAM spec was developed, especially for the usage or for having LCA lifecycle assessments of CCU and CCS technologies. Now, the scope of this document, it specifies requirements complementary to the ISO 14000 family for the lifecycle assessment of CO2 capture and utilization and CO2 capture and storage technologies and applications. This document was published recently in April 2025. Also, it's free to download, so please feel free to take a look at it if you want to. The document may serve as a template for transnational standardization activities by the new CEN-TC on CO2 capture, transportation, utilization, storage, and carbon accounting. It will promote the establishment of CCU and CCS technology by promoting their compatibility with LCS recommendations. And as mentioned, it was developed by GCI's director, Professor Volker Sick, and also co-authored and by Dr. Tim Langhorst, who wasn't able to join today as he assisted as co-chair and also took part in the development of the guidelines. As I mentioned, the document can be accessed for free, so for free download, and is a total of 34 pages. All right, what could be the next step? Taking a look at the time, I have to talk a bit faster, leave some aspects out, I'm sorry. So just very quickly, the next possible steps for the DIN spec 91508. So as the consortium decided to develop the DIN spec document, there's now the possibility to have this DIN spec as a new work item proposal, to have it either be taken into account by the German Mirror Committee, so the National Standards Committee, or to have it proposed into European or international technical committee on the topic, in order to, in the end, develop a document on the European or international level. So currently, Dr. Tim Langhorst is in contact with the German National Standards Mirror Committee on how to really address the topic in overall standardization. There were two more documents developed. I'll just skip this. It will be part of the slide deck to be shared. So two more documents, one on the topic of photocatalysis, and another DIN spec on the topic of a terminology surrounding the overall topic. Take-home messages very quickly. So there are different aspects of carbon management that can be addressed at the respective level of standardization, ensuring a precise and fitting dissemination of the state-of-the-art. Carbon management activities play an increasingly important role in effectively mitigating climate change, and developments in carbon management remain steady. So in addition to the continuous monitoring by standardization organizations to identify standardization needs, the sustained initiative and participation by experts, such as you maybe, or for example, from the Global CO2 Initiative, remains an invaluable necessity. Now closing with a final call to action. So it's up to you if you want to. We are glad for every expert that decides to really participate in standardization on his or her national level, the European or the international level. So your knowledge and commitment is crucial, as mentioned, as technical experts. Benefits include that you can get ahead of the game, so to say, by being part of a dynamic group of professionals proactively involved in developing standards. And your participation in the end helps to drive innovation, ensure quality and safety for the benefit of society, all while significantly fostering economic ties and prosperity worldwide. Here's some more context information for my colleague who is responsible for the mentioned carbon management activities. My contacts, also the contact information for Professor Volker Sick, responsible for DIN spec 91508, also for Dr. Tim Langhorst. And if you have questions related to the research project CO2 Wind Connect, please feel free to reach out to Mr. Dennis Kramer. All right, thank you for your attention.
Thank you, Stefan. Thank you very much. Interesting standardization is required for comparison of anything. So that's very good work. And now we can go to Anna. Just remember, if you have any questions, just please write it in the or in the Q&A box. And now I think it's time for Anna Petit, Dr. Anna Petit, that is postdoctoral researcher at UAB. So the floor is yours.
Thank you. Let me make sure that my screen is correctly shared. Okay. All right, so hello everyone. My name is Anna Petit-Bush and I am a postdoc at the Sostenible Research Group, which is part of the Institute of Environmental Science and Technology at UAB. And today I would like to share the work in progress that we are doing in a project that is called Confetti, and where we are doing carbon CO2 valorization to produce urea. So everything that I'm going to show you today is related to the environmental assessments, because like the previous speaker, I am not a technical expert. I'm more on the environmental side. So please bear with me if there are any more concrete topics that I don't touch upon. So what is Confetti? Confetti is a project that is trying to come up with a new technology that is composed of 3 different systems that aim to capture CO2 and nitrogen to produce urea as a fertilizer. It is meant to use, let's say, renewable energy because it's being powered by a microbial fuel cell. And it also aims to be a portable device. So through an electrochemical reactor, it aims to produce urea on site for whatever uses that are needed in agriculture. In general terms, Confetti has been presented as a potential comparative to the Haber-Bosch process. So in a way, trying to substitute or provide an alternative to the production of synthetic fertilizers. If you are aware of the process, the Haber-Bosch is very energy intensive because it has to capture nitrogen, atmospheric nitrogen, and it's very much using fossil fuels in all of the production lines. So thinking about this project was funded by a call, which is the Pathfinder Challenge, that very explicitly points out 2 requirements for these new technologies. On the one hand, if they are substituting for something else in terms of nitrogen production, for example, they must not use critical raw materials throughout the life cycle, and they also have to include a circular life cycle thinking approach in their conception. Based on these, we saw that there are a couple of challenges when addressing the environmental performance of the Confetti technologies. One of them is that it is a portable device, so the scale of operation is very small. And together with the low TRL in which it is working, it may be challenging to compare with a more competitive process such as the Haber-Bosch. On the other hand, a challenge is that we are developing new materials at the lab scale, such as new membranes for carbon capture. But at the same time, there might be some dependence on critical raw materials, even though we are not supposed to do that. So we are also relying on electronics to run the project, and that's why this could be challenging some of the original goals. However, with these challenges in mind, we also saw some opportunities. If we apply life cycle thinking from the beginning, we still have room for implementing modifications. So let's not do an LCA at the very end and just report a couple of numbers. Let's focus on the environmental performance of the products from the beginning and see what can be done. And the other opportunity is that we have a lot of primary data because we are an interdisciplinary team and we can rely on lab tests, on new developments that are being done by the technical experts. So with these in mind, we set out to develop an eco-design process that is aligned with the life cycle assessment of the 3 Confetti technologies. And we did that for 3 reasons. First, to identify if there were critical raw materials already from the beginning of the design stages. Second, to quantify the environmental impacts of these prototypes. And third, to evaluate how we can improve these prototypes through new strategies that can be integrated already through the design phase. So I have divided this presentation into 2 parts. The first part is related to how we define the eco-design criteria. So as you know, in any LCA, we need a scenario, a baseline scenario, in this case, a technology. But this technology has to be improved in a way, or we need to find parameters that can tell us if we are doing good or not and what could be done. So we set out this process by looking into the brand new regulation by the EU, which is the Eco-Design for Sustainable Products Regulation, which was released back in June last year. And we did that to align our progress as an innovation project with the regulations that are going to really establish what the products in the European market have to comply with. So this is a product of a brand new article that will be available soon. So if you need more information, we can provide that. So what we did was we looked into this regulation, and it is actually very vague. It has an annex where it sets out the type of parameters that need to be considered in the eco-design of any product. It doesn't specify yet what type of sector it is dealing with. This will come in the next few months. If you have heard, they are starting with the steel and textile industries. But since we are an innovative project working on fertilizers, we thought, let's align with that. So the first step was to translate those very general parameters into something more actionable for us as a project. To do that, we created this very integrated diagram, which takes the different life cycle stages of the individual confetti technologies from the raw material extraction to the end of life. And we tried to locate each and every parameter into the life cycles that they are affecting. For example, durability is affecting the use and maintenance, but there are others that are more transversal. For example, if we aim for a lightweight design, we are not only looking into the production of the technology, but also at the raw materials that are being involved. And with this, we have a very long set of strategies. Some of them are included within the production line. Others, as happens with life cycle assessment, are overarching, meaning that they can be affecting any life cycle stage. For example, any life cycle stage can be affected by the use of substances of concern, the consumption of energy, water, and resources, or on the other end, emissions to the air, water, or soil. So when we presented these to the technical partners, of course, it was very complex. There were too many parameters that not always can be assessed or are not relevant for each technology. So we set out on developing an eco-design process that was participatory with the rest of the partners. And I'm showing you here the example of the electrochemical reactor, which is the specific technology that captures the CO2 and generates the urea output. So to give you an idea, the diagram that I presented before contains about 36 parameters that can be measured or should be measured to report on the eco-design or the environmental status of the project and provide new strategies for the eco-design. However, some of these, for example, the release of microplastics, were very difficult for the partners to apply to their own project, or others did not make any difference for them because they were not affected. So we prioritized with them which were more understandable, which of them were more easily to measure, and which ones were more important for the product. And so for the case of the electrochemical reactor, we ended up with a set of 16 indicators that are on the parameter list and that can be measured for any LCA that you do, either at the inventory part, such as the consumption of materials, or at the impact assessment part with any impact category indicator. These are 16 that are fixed, that are set for any product that you need. However, there are other indicators that are called functional, which means that they depend on how the product works. For example, What is the technical life of the product? Well, this depends on how the product is designed or the function that it fulfills. Or what is the use of standard components or the steps for disassembling a product that needs to be repaired or recycled? So for the case of the electrochemical reactor, we defined 9 functional indicators that are deemed important. And these are the ones included here. The reason that I'm showing you this today is that we not only need to evaluate the typical indicators for the life cycle assessment, we typically need to understand the functions of the product, and therefore sometimes we need to model scenarios for very uncertain variables. Some of these very uncertain variables are these. For example, what is the number of cycles where I can use a membrane for capturing CO2? Sometimes we don't know that. Or how many standard components do I use? Well, maybe it can be measured in the lab or maybe not. So we have a challenge here, meaning that when modeling the environmental assessment of a product, how do we integrate all of these criteria? In our experience, we work very directly with the technical partners to see if this can be tested in the lab. However, it still remains at a very theoretical level sometimes because some of these data are not available or cannot be modeled by the technician at hand, right? So with these parameters, I want to show you an example that is actually pretty easy to evaluate, but sometimes not as straightforward as we may seem. So in the 16 LCA related indicators, there's one related to critical raw materials. You know, sometimes critical raw materials are not understood correctly. What is a critical raw material? For a non-expert, it may mean a material that is toxic. But if you look into the Critical Raw Materials Act of the European Union, a CRM is one that has a high supply risk and high economic importance because of its location or because of how important it is for a certain sector. So in the Confetti project, at the very beginning, we asked our partners which are the materials that are included in their products. And the first screening showed that there already are 12 critical or strategic raw materials included. This already gives a picture of how difficult it can be to comply with the eco-design criteria when we think about only the function of the technology, but not what it is composed of. So perhaps we think that we have a bio battery or that we are capturing CO2, and thus we are not relying on non-renewable resources or any type of other more critical material. However, when you look into the supply chain or into the materials involved, you realize that there may be a number of materials that need more assessment. Sometimes it can be difficult to remove them. That's the main issue, right? So it is not only about doing the life cycle assessment of the technology, accounting of the amount of each material, such as aluminum, vanadium, or copper, and the impact that they generate in terms of global warming potential or any other impact category, but also if they are strategically classified into a critical raw material or not. So if we cannot avoid the use of these materials for whichever reason, we need to for those or integrate eco-design strategies that help us recover them or characterize them better. So with this example, what I would like to show you is that on the one hand, there are criteria in the eco-design directive that may be at the beginning difficult to comply with, but that they directly lead us to other eco-design strategies that we can implement on the material side. So that was it for the more, let's say, eco-design part. With environmental assessment, I wanted to show you an example of one of these parts that I mentioned that could be critical in the sense of they could have a shorter lifespan, or they have a challenge in terms of measurement, or they are new and they are difficult to assess. And these are the membranes, which are based on ionic liquids for carbon capture. The main challenge here is that the synthesis of ionic liquids for carbon capture has very little literature out there in terms of life cycle assessments. If you look into the carbon capture technologies, they sometimes report that they use ionic liquids, but they don't always provide an inventory for these ionic liquids. They basically say that they are used, they are sometimes not modeled, only the energy of the technology is modeled. So here we have a huge gap in terms of understanding the wide variety of ionic liquids and membranes that can be used. So in our case, the first challenge was to characterize a sample of ionic liquids that are being used in the Confetti project to capture CO2 and transform it into urea. And we have two types. On the left, you see 5 ionic liquids that are being purchased. That means that you can buy them as ionic liquids in these 5 forms that I am showing you here. But the project is also developing new ionic liquids, meaning that they are developing the procedure in the lab to develop them, and we have absolutely no information about their composition and how the inventories look like. So to address this challenge, we have started the life cycle assessment, and we have 2 different goals. The first is to quantify and compare the environmental impacts of producing the ionic liquids only, so just the ionic liquid. And the next goal is to quantify and compare the impacts of the membrane. So the membrane is the polymer plus the ionic liquid, and that has the function of capturing carbon and producing urea. So with these 2 goals in mind, we set the system boundaries as follows. First, we have for goal 1, we need a huge characterization effort for the ionic liquids, meaning all the energy, water, and chemicals that are needed in the industry or in the lab to produce them. And then once we know these, we can merge them with the polymers to produce the membranes, and finally test if they can capture CO2 or not. So regarding the functional unit, here we had different options. For the first goal, we focused on assessing the impact of 1 kilogram of ionic liquid, and for the other one, the production of 1 membrane with a diameter of 1 centimeter. And here, there's another challenge again, which is the lifespan. Remember when I spoke about the criteria for the eco-design? Here it comes again at stake. What is the lifespan of a membrane that we have never produced and that we don't know how long it will last and how long it will capture CO2? So I will be solving these challenges as we go, so please bear with me. For the first challenge, how to address the inventories of these ionic liquids? Well, for the inventory analysis, we had to develop the life cycle tree. A life cycle tree depicts the synthesis route of each and every chemical component that is used for the production of one of these ionic liquids. On the left is the ionic liquid itself. On the right, you have the polymer that is used to produce the membrane. So we had to do this exercise for each and every ionic liquid, but as you can imagine, you have to trace each and every production line. So sometimes the information is not directly available, and this tree itself is full of assumptions. Although you have to follow stoichiometric balances, etc., sometimes you need to assume how it may be more often produced in the industry. Here in the diagram, what you see in green are the precursors that can already be found with an inventory in EcoInvent 3.10. So we had to go back to this point every time to identify where we can start. So to do this, as I mentioned, we relied on stoichiometric mass balances, a lot of literature data, but everything was very scattered data, a lot of patterns that were difficult to trace. And also, this is only for the materials. For water and energy, we had to rely on similar data in EcoInvent, which is sometimes very old, and it's difficult to trace as well. So in terms of limitations, we also had to deal with not knowing about the process inefficiencies, which had to be set at 95%, although we later did some sensitivity analysis. The catalysts and solvents could not be included, but sometimes they are reused several times, so that could be more or less justified. And also there are some byproducts that have to be modeled through economic allocation, which adds another layer to the uncertainty of these inventories. For the impact assessment, here we use 3 different methods for different reasons. One to compare with other literature, with previous projects, and with sister projects that are also doing a similar thing. So I want to show you a little bit the results. These are the average CO2 emissions of producing 1 kilogram of ionic liquid. You see that they are more or less similar and they align with the literature pretty much through the procedure that we developed. Some of this literature that we found was experimental. Ours not always was experimental. So we rely on this estimation, but it can be said that it's within the range. However, this doesn't give us much information, right? What we wanted was to inform the technical partners about what to do when they have to select one material that is more environmentally friendly. So we showed them the different trade-offs that happen when you choose one liquid or another. And finally, we identified that there are 3 of them that could be chosen to further develop the carbon capture technology, this electrochemical reactor, because they generate less environmental impact than the other options. Within that, we went one step further and wanted to know what was defining the impacts of these ionic liquids. So this is one of the 3 that were selected. And we saw that this gray part here in the graph is the anion of this ionic liquid. This anion is mainly composed of lithium nitride, which obviously has both a critical raw material and a very much impactful material as well. So the impacts here are very much taking up half of the impacts of the ionic liquid. And then other chloride and fluoromethane compounds that also have higher emissions. So with these, we recommended the partners to replace with nitrate ion. Now we're in the process of comparing this ionic liquid with the one that has another anion.
Hi, Anna. Sorry for interrupting. I think, yeah, the time is ticking. So
yes, I'm at the last slide.
Okay, perfect.
Yes, thank you. So finally, we wanted to check the membrane. The membrane has to be compared with the amount of CO2 that can be captured. And at the beginning, we saw that the impact of producing the membrane is almost 5 times higher than 5 orders of magnitude higher than the CO2 that it can capture. So here we needed to account for the lifespan and how many times we can regenerate a membrane. We did some tests in the lab, so the partners did, and this is one of the challenges that we can address through this eco-design process. So the partners are taking up the parameters that we suggested, implemented that in the lab, and then we can check that again through scenario modeling. So in conclusion, evaluating the environmental sustainability of these novel lab-scale technologies has extra complexity of the inventory phase. We need a lot of demands in terms of collaboration between technical partners and the life cycle analysts because the modeling is quite complex. And finally, if we have to scale up this LCA to industrial scale, it's also quite challenging because we don't have economies of scale. We have a lot of uncertainties and there's still much to do. And I'm sorry that it took a little bit longer. So thank you for your time.
Thank you, Anna. We can move fast to Jorge Zenan, Dr. Jorge Zenan, that is from the Biotechnological Center. Jorge.
Thank you very much, Juan. Let me share my screen. I think that everything is okay. Can you confirm it?
Yeah.
Okay.
Yeah.
So thank you very much to this webinar of Vivaldi. We were in charge of Work Package 5, the Sustainability and Circularity Assessment, and today I will present just one case study of Vivaldi that we performed with some colleges of Boku and Procession, and the work, Vivaldi process involve different steps, since the capture of the carbon dioxide from bio-based industries, its transformation in carbon one products like formic and methanol, and then the production of different organic acids, propionic, lactic acid, succinic, and itaconic acid, through fermentation of genetically modified Piria coli's, Piria pastoris bacteria. Another side, it was the nutrient recovery performed by UAB in terms of recovering different nutrients, nitrogen, but others from wastewaters. And today we will focus the case study of the production of itaconic acid. And according to the impact of the project, that it was mainly carbon capture for utilization technology, it was to reduce this carbon dioxide as a novel feedstock, trying to reduce the dependencies of fossil fuels, and reducing as well the effect in greenhouse emissions. The work that he presented was performed by a multidisciplinary team of VET as well. Here, Dianela was the mainly one developing the most technical part. But however, we would like to introduce what we understand and what are the technological backgrounds as well. Carbon capture for utilization technologies are pointed out as essential for critical technology to be developed in order to achieve the 2050 goal in terms of climate neutrality in the European Union, but as well has been pointed out by IPCC reports as one of technologies that could as well help in achieving these climate neutral goals. In this sense, the project and the work that the Boku and other Vivaldi colleges has performed is to develop these genetic engineered bacteria that they can transform some CO2-based products. Into this case that I will present today, itaconic acid. That itaconic acid is a building block that currently it has around 40,000 tons for production per year. It's not an important organic acid, which mainly root is a bio-based product, but as well it has as well an expectation to be rapidly with a rapid growth. No, it's higher than 5% of growth annually. So in this sense, to measure these technologies, we have to go to prospective LCA and safe and sustainable by design framework. What happens in case of the environmental performance of the technology when you try to measure them directly extracting the inventories and the data from low TRLs is that you normally overestimate, or you can overestimate the impact of the technologies, having the risk of rejecting a technology that in the future and in the scaling, it could provide a proper environmental outcome as well. This happens with the techno-economic analysis. So in this sense, prospective technologies are trying, it's a discipline that tries to understand the behavior of these technologies in a future point, understanding two main points, the potential upscaling and therefore the behavior of energy and mass input and output, and as well, which could be the conditions and interaction with the market that could happen in this future. And this is very valuable now for all this new SBD concept that is now combining the LCA, the economic analysis, as well with some safety and circularity conditions. But the core is this prospectivity, having in mind which are the potential consequences of a decision that can happen now. No? In this sense, the objective of this presentation is to understand and evaluate the potential of this itaconic acid production from bio-based CO2, from bio-based methanol, from an environmental perspective and the future scenario. So here you have more or less the concept. It has two main parts. First part is related to the fermentation of the process, and secondly, the down processing of the broth in order to extract all the itaconic acid that exists on the broth, but as well in a purified version, higher than 95% in this case. Most of the details of the process cannot be revealed in this presentation because of the confidentiality, but here you can see different inputs and outputs that are needed in this analysis, in this process. Since the water, the mineral medium for the growth of the strains, different alternatives of pH control, the water, energy, and so on. We have oriented analysis to the production of 1 kilogram of itaconic acid, and we include a 0-0 approach in terms of understanding the effect of biogenic carbon in the analysis, and we include the mineralization of it at the end of the life. It's important to show that here in this assessment, we combine two main points that are the ones that we understand that are the base for the prospective analysis. On one hand, we have the scaling up of the technologies that has been performed with SuperPro design, that is a chemical engineering software that allows us the upscaling of fermentation and then processing impacts. And on the other hand, we use eco-conveying background processes, but in this case, we had performed an analysis at 2030 and 2050 scenarios following image SSP2 conditions that are referred to the projected scenarios in which the decarbonization efforts in the European Union perform or influence in the market contour, having on the basis the decarbonization of the energy sector, but as well the decarbonization of the rest of the sectors because of this introduction of novelties. This has been performed for both on one side, the itaconic acid based on the CO2 production that we are studying in VIVALDI, but as well in the counterpart, that is in the itaconic acid benchmark that it comes from with the straw fermentation. So in this sense, we can observe and compare in a robust way the effect of decarbonization in our technology versus the other technology. We have performed the analysis using environmental footprint method 3.1, and we use the software Brainwave. Similarly to the presentation of an appetit, what happens in this kind of projects is that you are having new data from the laboratory results, but as well you have different cycles of modeling where you can identify different somehow hotspots in the technology that could be covered in further research or that could be covered even in the research during the project timeline. That means that we can project the technology in the best case scenario, that is which kind of evidence we have about the performance, for instance, of this fermentation. We can later on scaling up with this SuperPro design in this case, or chemical engineering toolbox, these life cycle inventories that we model, and then we use as well in this case, normalization with the bio-based counterpart in order to benchmark the hotspots. And with this, we close this loop iteratively, having this process of somehow improvement at early stages of the technology development. Here, just to show you some examples about what does it mean, the modeling in this kind of chemical engineering tools. Here we have an example of the fermentation. Normally, the fermentation, you can understand that there is this bacteria, but in order to reach out some volumes of broth or minimum volumes of these bacteria that can produce the itaconic acid, you need a sequence of reactors in order to increase this strain's growth, or foment or boost this strain growth, that later on it could be applied in the fermentation to produce the itaconic acid. So we have here the sequence of reactors that is needed for the supply, but as well in this sequence of batch reactions for the broad growth, in order to have the final volume that will be the reactor, the batch reactor that will develop the itaconic acid by itself. Here, there are some examples about how we perform the scenarios and how was developed the reasoning behind the analysis of these fermentation technologies. As you see here, we have 4 scenarios where the titer, that is the concentration of itaconic acid that was reached out, was increased during the project. As well, we have some glycerol, that this glycerol is supplied in order to start the reaction. And here you see how we model a fossil-based glycerol, that is the one that is used in the laboratory, but as well how this influence if we move towards a bio-based counterpart. The pH control agent was evidenced as a key factor. We moved from potassium hydroxide to calcium hydroxide, and as well we model some changes in the down processing efficiency, moving from 75 to 90%. It's important as well to see how the heat supply, in particular in the down processes, can affect from steam or fossil fuel sources of heat towards electric ones. As well, in terms of heating, what is the role of heat integration and water recovery? This was as well assessed in terms of modeling and included in the models. And all these scenarios were modeled in these 2 time horizons that I mentioned in terms of having this background and control conditions of the market at 2030, 2050. Here you can see how the titer affects to the impact. You can see this first iterations that we have seen how the titer was improved. No, and here we observe how much relevant was this aspect and this KPI in order to evaluate this technology. But if we move to the high titer, the final scenario, here as well, we were able to observe the different influence of the different hotspots. So here we observe critical points as the glycerol or the methanol, potassium hydroxide, and so on. You can see that they can differ in terms of contribution and percentage, the different categories of the environmental footprint method. You have acidification, climate change, and so on. But just to show that these 6 main parameters or processes were the main contributors in most of the conditions. No? As well, we use the normalization in order to benchmark. Here we are benchmarking with the bio-based counterpart. Here we have the 4th iteration with high titer, and you see how in climate change we were below 1. That means that we were reducing the impact in comparison with the counterpart, but there were some trade-offs in other categories due to different conditions that we were able as well to identify in previous hotspot analysis. No? What we did is improve these scenarios in the 5th iteration, where we include this bio-based glycerol, where we include the substitution of this pH agent and so on. And we found that the potential of this technology, rather than the one that was observed somehow in the translation of the lab experiments, it can improve importantly with these improvements that I present in the previous tables. No, important that I will go now into some details. No, but you can see now how in all the cases the technology could be improved in most of the impact categories. Here, just to focus the discussion, no, and represent how the different contributors affect in these improvements. You can see here the climate change, global warming potential impact category. You can see on the right side the benchmark, the bio-based itaconic acid, and you can see the first block, 2030, 2050 scenarios for the 4th interaction and the 5th interaction, that is the improved one. It's important to see how the electricity supply and the efficiency increase allows the reduction of the impact, but as well other conditions like the glycerol substitution. Here you can see these boxes on the top, that these black boxes that illustrates the emissions of the carbon dioxide in the oxidation of this glycerol that affects not just in terms of consumption of glycerol, but as well in the emissions of the oxidation of this glycerol. This affects importantly in climate change. So the substitution of these fossil-based with bio-based counterparts, that is something that already some of the researchers told me that they tested in other projects, is an important improvement in terms of climate change or global potential. We see as well how the methanol it's an important contributor. That means that the yield in how much carbon moles are transformed into the final product are relevant, but as well the source of this carbon dioxide methanol. Of course, other methanol sources could be explored in this sense, not like bio-based, but it's interesting to explore how this affects, and how we see in the improved scenarios is mostly the limiting factor and the major contributor in this category. As well, is not neglectable. It's important the pH control agent, that in this case we had a couple of strategies that were followed. The first one is the substitution of potassium hydroxide with calcium hydroxide, and the second one is the reduction of the pH at the one that the strains can operate. That influences in the pKi equilibrium. That means as well in the need of these basics to control the pH. So this is some of the insights that we provide for one case study in VIVALDI, and just to show some conclusions, the prospective assessment provides a resourceful framework for identifying hotspots and drivers at early stages that are very meaningful in terms of how much then you can define and later stages of the research and KPIs, in this case for itaconic production. We highlighted the potential of the itaconic acid production through this route of modified coffee bacteria based on the CO2-based methanol. Well, we think that it's important as well how we observe the synergies between the improvements of the that can be performed at genetic level in the environmental outcome of the results, in both in terms of titer, but as well in terms of operating conditions that allow a reduction in terms of resources and therefore in other environmental impacts. And as well, we observe how much it's important the comparison in these future-oriented scenarios, because it allows us to benchmark and see how the technologies can be projected, both the CO2-based in this case with the bio-based counterpart, and allow us this benchmark in a robust way. And this is end of the presentation, and I open to questions and to have a great discussion with you. Thank you very much.
Thank you, Jorge. I think that we have some minutes for some questions. And the first one was, I think, for Stefan, was from Angel Puente. Thank you, Angel, for your question. And I don't know if you can read, Stefan, or I should read?
Yes, I'm looking for the question. I'm sorry. Okay. So it's in the chat.
In the Q&A box.
Q&A box.
Yeah.
I'm sorry, where can I find it?
We can read if you want the question.
Okay, thank you.
That's easier. So DIN spec 91508 does not have a final position on how to allocate CO2 avoidance burden between the CO2 supplier and the CO2 user. The global CO2 guideline seems to be a clear preference. other plans to include a more specific provision or decision on this in 91/508 in the future?
Okay, good question. Again, unfortunately, I'm no technical expert. So there is the option, as I mentioned, to revise the documents. So this usually takes place after 3 years. So this could be, for example, an aspect that could be addressed in a future revision. As it's a technical question, I would maybe recommend to contact Dr. Tim Langhorst with this question. Maybe Lara, I don't know if his contact information is present on the webinar site.
O sigui que digue'm algo ràpid.
Sorry, Albert, I need to. No, we don't have the contact emails for privacy reason on the website. But what I would suggest in this case is to put, or I can send him directly this question.
Yeah, maybe.
The name of the person who answered the question.
Yeah.
Or we can put this question as a comment on LinkedIn and then he can answer there directly.
Okay, yeah, would both be options. Thank you for that. Yeah.
Thank you. Thank you. And the other question was for Jorge. Jorge, can you read that?
It's just
Are you referring to the considering to my Angel Puente question?
Yes.
Yeah.
Well, Angel is asking about the potential, if we are in favor or not, about the credits to the carbon dioxide removal and who could be allocated and so on. This is a very relevant discussion about the CCU technologies. Here there are a few conditions. I think that there is not a yes or no answering. First one is what we have in terms of economics, because I think that is important to allocate or not the environmental burdens or not related to the economic consequences and business models. Now, the current regulations of carbon dioxide removals are mentioning that there is not any credit for those technologies which products they do not have a longer lifespan rather than 35 years. That would exclude potentially these VIVALDI technologies, for instance, because in this case we are thinking in plastics that it depends on the plastic, but it's not mainly oriented to long-lasting products, no? So in this case, this credit could not be allocated, I would say. In our analysis, if you have seen, we are considering the thorough burden assumption in this sense. But it's something that could be discussed. However, it's important to say that in CCU technologies, the temporary aspect is relevant and it has to be considered as a breaking point in terms of as the main criteria in order to allocate or not these credits. Otherwise, you can provide some carbon credits to some products that are not somehow storing. They are in a very fast loop. What it happens in the use of biogenic carbon, and it's not the case of itaconic acid because it has a bio-based benchmark, but we've had the example in other slides of succinic acid where there is a fossil-based counterpart, is that if you extend the system boundaries, and is the proper way to do it with the end of life of the product, of the CO2-based product, then you can see the emission and the release or not of this biogenic carbon that is neutral versus the net emission that happens with a fossil-based counterpart. That happens even in a 0-0 approach or a -1+1 approach. It doesn't matter if you exclude the biogenic carbon or if you include the capture and then the release. The balance could be numerically the same. Although there are some conceptualizations or different conceptualizations that can differ, numerically the effect is the same if you include this end of life, no? That we did it.
Thank you, Jorge. There is another question for you from Atakan Larsin. I was wondering whether you were able to also look at the other SST RCP pathways. Do you expect similar results on their pathways or will the outcomes differ significantly?
Indeed. This is an uncertainty, of course. Making the systems and the models more complex, as in this case with premise package, and having these integrated assessment models behind these background processes can create some uncertainties because, well, it's future. We don't have a crystal ball to say that this is the future. Potentially, there can be some differences in the use of different pathways, but we think that the one that we use is the most consistent one, and they probably do not differ as much as expected. You think as well in the uncertainty that we are as well measuring 2030, 2050 scenarios, we are mostly interpreting this as a range of how much could be affected and how much could this impact be in the future. Of course, this uncertainty is inherent to these prospective scenarios, but I could say that the final decision making, that in this case is to accept that this technology has a potential to be upscaled, this decision making could not change with this change, because as well the margins that we observe with all these improvements that are potentially behind are very important, in particular for climate change, but not uniquely.
Okay, thank you. We don't have any more questions by now. I don't know if any of you have another question or wants to make any remark. Otherwise, if not, I have one, so I can do it. So you are trying to get some certainty from the uncertainty. I mean, you have many things that can change. So how can you be sure that your selection of the best process is really the best process and under what conditions? I mean, we have modeling, we have sensitivity analysis of this of the decisions, and maybe you have similar techniques that you are applying. So
I don't know if Anna, you want to as well to respond to this question, or
yeah, for any of you, because you are working with very and also we are working with multi-criteria things. So sometimes it's not a clear black or white thing. It's a gray scale with many different things. So what you have to do with when you have different criteria and they are contradictory?
I think you always have to be transparent about that. If the issue is that you have trade-offs either way, and you cannot make a decision that is either black or white, well, we usually say that LCA is not like yes or no. It's always like it depends, right? So I think that actually doing the sensitivity analysis, as you mentioned, and being transparent about the multiple effects that different parameters can have is one of the ways of showing that you really took care of it, that you not only made an assumption, but that it was properly modeled in a way that shows some trend somehow. But either way, in the future scenarios that Jorge was telling you about, I think it's even more difficult, right, to show what will happen in the future.
Well, what is clear is that we need a clear framework to compare, and that's why Stefan should say something to us about how to standardize all these things. If it's possible to standardize all these things or these criteria, or maybe too much work for them, for DIN.
So yeah, basically every, let's say, product and process can be standardized. So it really depends on your expertise, what you think could be beneficial, so to say, to have standardized. Yeah, so please feel free, of course, also afterwards to reach out to me if you have any ideas for standardization. And yeah, I take a look at it.
So thank you thank you to all the speakers, and thank you, Stefan, Anna, and Jorge, and thank you to Lara for organizing everything. So thank you to CO2 Value Europe. So I don't know if Lara wants to say bye.
Yeah, just one thing maybe. The recording and the presentation will be available on the Vivaldi website and social media channel in the coming days. So I suggest you all to monitor our LinkedIn page. I will post now the link so you can check it and you will be updated. Of course, if you are thinking also of any other question, that's the right spot where to put them, and then our speakers and team as well can have a look at them and answer there. So thank you all really for your time and expertise, and Juan as well for the moderation.
Thank you for the attendees. Of course, thank you for joining.
Thank you.
Thank you.
Thank you very much.
Thank you, bye.
All of you.